Our next speaker is going to be Alessandro, and we're going to talk about performance profiling with eBPF.
Hello everyone, I am Alessandro, and today I'm going to show you how to write a performance profiler with eBPF. I'm going to show you Aya. Aya is a project I work on with other people, and it's a library to deal with eBPF from Rust. With Aya, not only you can use eBPF from Rust, but you can also write the eBPF programs themselves in Rust, compile them to eBPF, and then they get uploaded to the kernel and they run. So it's a way to write kernel code with Rust. So that's the link to the main repo. We also maintain a lot of related projects. We wrote the target for the Rust C compiler for eBPF. We wrote a linker. We have a fork of Wasmtime because we're looking into things. So we do a lot of things. If you're interested, please take a look. That's our Discord. On Discord, we help people get started with eBPF and write their own programs, and also we discuss what we work on, the roadmap and everything. So if you want, please join. First, very briefly, something about. So first of all, who knows what eBPF is? Okay, awesome. Who has used eBPF? Ah, amazing. Okay, so for all the others, eBPF is essentially a bytecode format which is understood by the kernel. You can think of eBPF as the WebAssembly of the kernel. So in the same way that you can compile different languages to WebAssembly and then load those modules inside browsers, you can do the same with eBPF for the kernel. So you can use C or Rust or Elixir as of 2 weeks ago to write programs that get compiled to eBPF and then they run as part of the kernel, okay? More broadly, it's also a set of APIs that the kernel will provide to these eBPF modules that you write. I will show you some examples of APIs that we're going to use for profiling. And it's essentially the modern way to extend the kernel to write new functionalities, to implement new policies, networking policies or security policies, or any way that you might want to customize the kernel. Who knows what a profiler is? Okay, so profilers are programs to trace and monitor execution of programs. You can profile CPU usage, memory, any kind of resource usage, memory allocation, whatever. There are different kinds of profilers. If you, for example, use Python or Node.js, they have profiling infrastructure built inside the virtual machines. So as your program gets executed, if you have profiling enabled, it will hit those special functions in the code. Those functions will generate samples for your program. And based on those samples, you will be able to tell where your program is spending the most time and stuff like that. But for profiling native code, so the kind of code that you get by compiling Rust, the main two kinds of profilers are instrumenting profilers, which are like part libraries, part tools. The library bit of the profiler essentially gets compiled into your program, either by you manually inserting calls to the profiler, or by the compiler, like GCC, inserting instrumentation code inside your program. And then as your program runs, this library profiler code will generate samples for then the profiler reporting UI to use. Or there are sampling profilers, which tend to be separate and be completely separate from the programs you're analyzing. The way these profilers work is that they will somehow observe the state of a program externally as the program is running. If they're good profilers, they will have very little overhead. So the advantage of using this kind of profilers is that you can, for example, run it in production, right? It will not disturb the production code. And the way they work is that they will sample the program execution at a given sample rate. So every few times per second, they will take a snapshot of the program, of what it's doing. And then by aggregating all these samples, you will be able to tell where the program spends the most time or allocates the most memory and that kind of stuff. So what prompted me to give this talk today is that for work, I work on a tool that I run several times per hour. Like I hack on this tool, I add prints when I'm debugging something, and then I recompile and then I rerun it. Whenever I rerun it, this tool takes about 5 minutes to extract a tarball of 52 gigabytes. So anytime I do something, I recompile, I start it with 5 minutes, see if my fix works. Otherwise, I change something, recompile with 5 minutes, This gets very boring very quickly. So 2 weeks ago, finally, I decided, okay, I'm going to make it faster. I'm going to see if I can make this part faster. As I said, this part of the program is extracting a very large tarball. So I decided to take tar, which is like the official tool to unpack a tarball and see how long it takes on that snapshot, right? I figured this is the tool for the job. It's going to give me a baseline of how fast this can be, and I'm going to see if I can make it faster. So on that particular snapshot, as you can see, tar takes 4 minutes and 15 seconds. It reads from this. At the bottom, you can see a screenshot of IOTop, which is like a Linux utility to monitor disk activity. So while tar is extracting this tarball, it's reading at 125 megabytes per second, and it's writing at 407 megabytes per second. Now, this snapshot is compressed using ZStandard, which is a compression library from Facebook. ZStandard, they claim that they can uncompress at 1.5 gigabyte per second, right? So by looking at that, I figured, okay, tar is not getting nearly close to the bottleneck to ZStandard, meaning there's surely a lot of room for improvement, right? And after 2 weeks, and after using the profiler that I'm going to show you, this is where we are now. I wrote a new tar command in Rust, and on the same snapshot, it takes 1 minute and 37 seconds, which is about 3 times as fast as tar. It reads at 500 megabytes per second, and it writes at over the 1.6 gigabytes per second that ZStandard does. How did I do this? First, I started profiling with Perf, which is the standard profiler for Linux. Perf is actually part of the kernel, so there is a whole Perf infrastructure inside the kernel. And then there is a user space command that you use to record your programs and to analyze them. This screenshot is a screenshot of the perf report command, which is what you run after recording a process. And as you can see, it shows you call stacks. And at the bottom, I have expanded one call stack. So I have expanded the main function, and I see that I'm calling an unpack in with IO function and that. And perf is workable. So whenever I profile something, I usually start with perf. But then if I realize, okay, I'm going to spend like a week or two on this thing, what I usually do is I write custom ad hoc profilers. And today I'll show you how to write one. The core logic of the profiler, as I said, is we need a time source so that we can sample it at a given frequency. So we establish a time source. In this case, we're going to use the CPU clock counter provided by the Linux kernel. This counter is essentially like just a number that goes up anytime a CPU clock ticks. And we just use this as a time source, and we say, okay, we want to sample this, in this specific case, 500 times per second. When we sample it, we're going to execute an eBPF program that will see what the program we're monitoring is doing. It will dump a call stack, and we'll send it to user space, and there we analyze it, okay? So this is the eBPF program. This is just like regular Rust. This is using the II eBPF API. It's one function call. It takes one argument, which is like a context provided by the kernel. And then it calls the doSample function, which does the actual sampling logic. I will show you the code for the doSample. But the notable thing to see here is that it's just regular Rust code. It gets compiled to eBPF, and this ends up running in the kernel. So when this executes, it's not running in user space like any regular program. The kernel actually execute this code, right? Which is pretty cool. So what I showed before was the eBPF code. Now this is the corresponding user space code. Most eBPF programs have a user space side and a kernel space side. And what you can see at the top, we start by loading this ngmi file. It's an ELF file compiled with eBPF machine code. We load it, and then we extract the perf at the bottom. We extract the perf samples function that I showed before. We load it into the kernel, and we attach it to the perf count software CPU clock time source, as I said, and we say, okay, we want to sample it 500 times per second. Okay. Now this is the actual sampling logic. I don't know. Yeah, you can see it. It's very simple. At the top, it defines a map. eBPF maps are just data structures that kernel space and user space can use to exchange data, essentially. And what the doSample function does is it will create a new event. It will call the BPF get stack function. BPF get stuck it's what's called a helper, and it's one of the APIs exposed by the kernel to eBPF programs. It will call that function. That function will return a list of instruction addresses leading to the current call, essentially. So we take that list and we just send it to user space, okay? In user space, we take that same map. The map is an iterator. We scan it, and then for each event, we pop an event and we parse it. I'm not going to show the processing code because it involves debug symbols and a lot of like really boring stuff. But you can imagine that the simplest way to process an event that would be sent by our profiler would be to just dump it out on standard out. And so if we did that, we will get a list of function addresses, essentially, right? And if you symbolicate these function addresses, you get a stack trace, essentially, right? Now, up until here, we have a working profiler. The profiler will be able to monitor the program we're monitoring anytime it's executing on any CPU. But if the program is sleeping, so say that in your program you call std thread sleep, we will not get any samples of that program while it's sleeping, right? Because it's not on any CPU. So like when we sample the time source, the Linux scheduler will be executing other stuff because our program is sleeping, right? It's the whole point. It's not executing. So what we can do to also see the time that our program is spending not executing, which is called off CPU time, with eBPF, we can instrument the sched switch kernel function. So anytime the Linux scheduler is going to switch out a process from a CPU and it's going to switch in a new process, we take a snapshot of the program right before it's switched out. So say that a program calls sleep. The kernel says, okay, you want to sleep, I'm going to switch you out. We take a sample there, okay, deterministically. So we know when a program stops. And then the next time the program is put back in on the CPU, we know for how long we slept. And we are able to say, okay, now we're seeing new samples. In that gap where we saw no samples, we know that we were doing the last thing we did when we instrumented the sched switch program. And so this allows you to see off CPU samples. Imagine that you have a multi-threaded program where multiple threads are using locks and doing some kind of communication. Some of the time they will be sleeping, right? So because like locks will be contended, or like they will be using channels, and so the channels will also be contended, and so they will sleep. By using a profiler that can sample off CPU samples, you can actually see when your program is sleeping. The reason why I did this is that, remember at the beginning I showed you that tar was reading and writing well below the limits of Z standard and my disk capacity. And so I figured I need to see why it's sleeping, why my program is actually not executing, why it's not looping on decompressing, and so decompressing as fast as possible, right? So I did that, and by doing that I realized, okay, my program is sleeping a lot on doing disk I/O, okay? This would be too long to discuss, but like Linux implements various caches, and in order for your program to be as fast as possible, you need to be hitting those caches and never hit disk directly. If you hit disk directly, you're going to sleep, and you don't want to do that if you're trying to maximize performance, right? So I wrote more eBPF code to also instrument when disk access starts and when it ends, and I was able to plot. I'll show you how to plot stuff. To plot the throughput that my program was achieving. And then with that, I was able to improve things a lot. And then I saw that I was still having too many page faults. So I also instrumented where the kernel handles page faults. And I implemented some custom logic so that I was only looking at page faults when they were coming from this file cache used by the kernel. So not all page faults, because there will be way too many. Like a program is page faulting as it pages in memory all the time. I was only interested in seeing the page faults that were resulting from trying to access a file that was not hitting the file cache. So I implemented all this logic with eBPF. And then now this is profiler.firefox.com. This is the best, this is my favorite website on the internet. Nobody knows about it. It's the profiler used by Firefox. It's also the profiler used by the Firefox DevTools. And it's also deployed as a standalone app, right? It supports many formats, and it has its own custom format. So I made my profiler output all the samples using this format, and this is the result. This is much better than what I showed at the beginning with perf, right? You can see you get a breakdown of all the samples by thread, you get memory usage, you get call stacks, you get source code of your program, you get like the samples with line accuracy of where your program is spending time, you get a disassembly of your program. This is amazing. You get flame graphs. This is literally the best app on the internet. And that's my talk. So that's Aya. And again, please join Discord if you're interested.
So where do you draw the line between what you decide to write in eBPF and what you write in user space? So like what's the use case? Like why wouldn't you, for example, write your supertar in just eBPF in the kernel and not even bother to write it in user space?
Yeah. So you can, with eBPF, you can literally attach to any place in the kernel, and you can implement your own custom logic, but the eBPF code is limited in many ways. It cannot allocate memory, it cannot panic, it cannot loop for too long, because this whole eBPF project is only safe to execute at the kernel layer if the kernel can verify when you upload a program before it starts executing that your code is safe, it executes quickly, and so it's not going to cause kernel overhead, right? So, but it's a good question, because the way I managed to make my program so fast, if you see this picture, there are a bunch of threads. In my profile, I'm marking kernel samples in yellow and user space samples in gray. If you see all those threads, they are just yellow. That is IOU ring. And IOU ring is this amazing new technology in the kernel that essentially allows you to spawn kernel thread in user space. And so that's what I'm doing actually. Like I'm offloading all the disk activity to kernel threads. My user space program thread is at the top, it's all gray. And you can see there is a tiny yellow line, and those are just the IOU ring calls. So I'm just going in the kernel to tell uring, do this bunch of stuff in the kernel.
Hey, thanks, that's really cool. Building a supercharged profile, a sampling profile using eBPF. Sorry, get close to the mic. I've used a sampling profile on UShift on Windows, which isn't as cool as that because it can't. But I was just wondering, with the instrumenting profiles, do you have any recommendations for instrumenting profiles for Rust? Because I was looking for a bit and I couldn't really find anything.
Yeah. So first of all, I only work on Linux. Sorry.
Okay. All right.
So on Linux, perf is great. Like perf is really great. I think that there's a wiki page on the Arch wiki thingy about perf, and it's like 20 pages long. So perf is great. It's not easy to use, but if you know how to use it, you can do everything that I've done with perf as well, using different commands. It's just not as nice, and it's you need to know a lot more things. You need to know how to use it. It's not a it's a tool written by kernel developers for kernel developers. So.
Oh no, my question is about instrumenting profiles.
Yeah. Oh, instrumenting profiling.
Yeah, so I've used a sampling profiler on Windows. Which looks similar to that, at least that first screen of perf.
There is only one instrumenting profiler that is worth being used, and it's the one in the Google Perf Tools repository, and it outputs a gprof format, which is like a standard sample format, and it's fairly low overhead. That one, yeah. It's if you Google gperf tools, it's part of that suite of tools.
Thanks.
You mentioned that you can check when a thread does a main memory access and goes to sleep because it takes time to get that memory in.
Yeah.
Do you know if Rust async runtimes use this feature to swap threads, and is that something that could be done?
So the kernel will do that for you. So if your thread accesses, if your thread behind a task accesses a page that is not there, and so it needs to do I/O, that will get suspended. The thread will get suspended.
Okay.
Yeah.
Yeah, we've got a question from Discord, and so Snappy's asking, what did you find in tar, and why is tar faster?
So tar is a terrible format.
Terrible format?
I had no clue how tar worked until 2 weeks ago, and now I'm like, sorry to be the maximum expert in tar. What makes tar terrible is that it was invented before we all were born, and so it's meant for serial decompression, right? And so that in itself puts a limit on how fast you can go, because like if you need to serially unpack something, then you cannot parallelize it among threads with Rayon, for example. one of the biggest issues with tar is that by being a terrible format, you need to do so many syscalls every time you unpack an entry, every time you unpack one single file from the tarball. The tar RS crate will do something like 10 syscalls, and if you want to go fast, you don't need to do syscalls, right? The reason why this is fast is that it does like one syscall every 3 seconds or so, you know? And so that's one of the reasons. And also simply because like tar was written a long time ago and people didn't care, or like people didn't have tools to, like IOU ring didn't exist. It's something that was invented like 2 years ago, you know? And so, yeah. But that said, like even before I started using IOU ring, by just memory mapping the input file to tar, that cut like 20 seconds. So GNU tar could at the very least do that. Yeah.
Awesome. Hey, thank you so much.
Thank you.